He was graduated from the Department of Mechanical Engineering, University of Ceylon. He has obtained his PhD from Cranfield University, UK. He has over 20 years of experience working in the R&D, manufacture, and marketing of agricultural implements. He is also a retired senior lecturer in agricultural and plantation engineering at the Open University of Sri Lanka. He was a consultant to UNDP and was a consultant in establishing engineering faculties in the University of Sri Jayewardenepura and Southeastern University of Sri Lanka. He is none other than Dr. Gamini Kulathunga. Sir, the time is yours to enlighten us with your invaluable knowledge and experience.
Thank you. One of you will have to upload my slides as I speak. Before you put the slides on, yeah, okay, leave it there. Before I start on with my slides, I think I'll have to say something a bit more about my experience related to design. In all, I think I have put in about 50 years of engineering, half of it in the industry, half of it in the academia. And at the moment, we are also helping IESL and Jayewardenepura University in their design work with engineers and with students. So I'm going to talk based on that experience and my work experience. And before I start, I want to dispel some of the myths regarding ingenuity, intelligence, and creativity. It is not age or gender related. We have to understand that first and foremost. There was a time that gender played a big role in engineering, but now it is not so. And also we get carried away with this high-low technology division. Actually, if the technology is the one that is correctly applied, there's no high or low. And a very good example of it is Vidyajyoti Ray Vijayawardena, who started his invention with a two-wheel tractor, Landmaster, which later he went to UK to popularize. And then he also at the same time he built aircraft. This gyrocopter that he built was used in one of the James Bond films. So I would say that he had his feet on the ground and reached to the sky. That should be the way. Looking at some of the presentations, except for one or two, they are mostly, but I would say within inverted commas, high-tech. That might be partly reflecting on my background 50 years ago. Whatever you are talking is high-tech to me now. And one more thing, this rewards. Of course, you are taking part in a competition, which I understand. But this creativity, ingenuity, and thinking outside the box can be killed by competition. Especially if the wrong type of rewards are given, if there are enough recorded evidence to show that it kills creativity. So you have to be mindful about that in the future. And also in a way, the panel evaluating, we have to keep that in mind. Regarding today's presentations, so three had some prototype built, which is I thought is essential. Others, I would put it in the category of conceptual design. So it is up to the panel to decide between the two. Okay, let's go to the first slide. Yeah, these to drive show a slight difference between innovations and invention. Though we are trying to elect an inventor, it could be an innovator. Difference is very subtle. Some of the inventions can be innovated. So that is subtle. And also they are not confined to products, not gadgets, what we call artifacts. It can be processes. And re-engineering a process, removing redundancies, new use of existing method, they are all come under innovation. They also must be given equal weight as much as inventions A strict invention is something that no one else has done. In my view, we must not judge university creativity with invention. I would rather go for innovation, because inventions, patent, that that game is too much for you. That is my personal view. I think you can, ISL can consider that. Can we go to the next slide, please? Project learning. This project learning is something that you do, I think, with certain universities call it design project. Foreign universities call it service learning in engineering. That means you are doing something to service the community. It's called service learning in engineering. But I didn't use the word here because engineering services, you might misunderstand it for engineering services, but it is something else, service learning. So we can call it project learning for our use. That places knowledge in a particular context, what we call situated. The knowledge you have gathered in the university has to be now situated in a particular context. So that is where the project comes. You have to identify a problem, find a solution. The problem identification is yours. So that problem identification is contextual. It's always done in a context. It is not a mental exercise. It is not a conceptual exercise. It's a reality. It's a reality exercise. Then we also, I think, we learn subjects like thermodynamics, hydraulic properties of material, metallurgy, etc., etc. When it comes to real project work, these have to be drawn, they have to be combined and integrated to find solutions. And for that, we use metaphors and analogies to draw from one field to another field. I will explain it with later with what I have done in my career. Then this other danger is, I sense it in your design presentation also, what we call by Abraham Kaplan calls it law of instrument, and Maslow calls it hammer theory. That is basically what it says is hammer theory. You will understand, because it says that if you are very familiar with a hammer and in your toolbox, you have mainly you have a hammer. Then whatever is you use it irrespective of its use. I mean, everything looks like a nail and it looks like needing hammering. So the hammer becomes the tool for you. It's a very crude example, but then this applies to subjects, even in theory, even in research. People use the process knowledge base they have for an inappropriate application. That is called, and but you don't get caught in that. That will make your creativity almost nil if you get caught into this hammer theory. Can we go to the next slide, please? Accreditation. Yeah, this I introduced because this what we are going through now, doing designs and taking part in the competition, all right, and doing designs and doing project work in the university, whether you take part in a design competition or not, is preparing you for professional qualification, for accreditation as a professional engineer. And that accreditation requires some skills that a normal university curriculum doesn't provide. So that is where the needs for project work and design work and problem identification creativity comes in, because to become a professional engineer and to be accredited, you need these things, and basically it means you have to match your knowledge with reality. We do something, professional engineers do something called a reality check. That if you do some calculation and end up with a figure, you just look at the figure irrespective of the calculation and the data, you look at the figure and say, is this real? It's called a reality check. So matching what you are doing to reality is an important part of this whole work. And also it involves sort of virtually lifelong learning, because it's a continuous learning process. For a professional engineer, it's a continuous learning process. It never ends. I mean, it never ends with, I mean, it will end when you retire or whatever. But it's a very circular feedback process that keeps on enhancing your life skill. Okay, next. This I try to give schematically some sort of a hierarchical order of engineering knowledge or engineering pedagogy. But this is not very strict thing. You can, this thing, what I given here, you can call it engineering science, engineering technology, and pure technology, whatever you call it. But there's a distinct difference among these. The first one, the science, is sort of a conceptual, imagination, conceptual oriented. Of course, it has a practical element, but basically it is conceptual, heavily conceptual. When it comes to engineering, it is heavily application oriented. You are applying the science of engineering to things to study or to do or to analyze. You are application oriented. Then when it comes to technology, which is another ball game, it covers everything. It covers science, engineering, the things available, things people do, culture, economy, all that. And what you do is what is called acceptable thing. That what you do has to be acceptable in a particular milieu of culture, economy, technology level, educational level. So that technology is a very, in all, a complex thing than the first two. The first one is, I would call it sort of intuition based, because you go by feelings and you try to, you get a hypothesis and you test it and see whether it's true or not. Sort of, it comes from your imagination. The second one is like more like solid knowledge, based on knowledge of reality and practical experience and things like that. And the last one is the real doing of it. I don't know whether you are aware that long before science and engineering evolved, what ran the world is technology. People who have done thermodynamics will know that the steam engines were there long before thermodynamics and these various steam cycles and everything were known. Steam engines were, so the science and technology evolved from science and engineering evolved from technology, the real doing part of it. I would call the first part, the science part, like the bones of a living being, the engineering part, the flesh, and the technology is what we call fascia. Fascia is the thing that collects all the bones, flesh, and everything and makes you a living being. Your bones and flesh will not make you a living being. The fascia is the thing that connects everything to make you into a living being. So technology, in my book, my understanding is the highest of it. And it can be seen in very well-known institutions like MIT, IIT, Imperial College of London, AIT. They are all technology-based. They are not science-based, no engineering-based. So we have this, we have Sri Lankan and our education system, our education system, the academia has this right mental problem of thinking engineering is the highest achievement. I don't think technology is the highest achievement. Shall we go to the next one? This again is a schematic diagram. Don't go by these schematic diagrams. These ideas are, they're not generated in boxes like that. They come and go in various forms. This circular thing I had drawn can start anywhere, end anywhere. It can be clockwise, anti-clockwise. The arrows can be upward, downward, anything. So this idea generation is not given in a book. You know, it is something that happens to people. So though I have given it in this type of a schematic diagram, it is only a schematic diagram to understand the components, but the components are not connected like this in a linear fashion. What is not there is the intuition and the tacit knowledge. Tacit knowledge is something you cannot express. You can put it in a book and tell someone, but you know it. Intuition is something like that. Though in the universities and in your normal academia, we don't talk about intuition. If you read about scientists, inventors, and engineers who have done for contribution, their basis, their starting point is intuition, not theory, not knowledge. Because they have to make informed assumptions, do some approximation, because you are not doing science, you are not doing scientific investigation. You are trying to make something. So you have to make assumptions, you have to make approximations, and imagination plays a very, very big role in that. Of course, as we proceed with imagination, it has to be supported by fact, data, experience, calculation, theory, etc. But they come much, much later down the line. I don't know whether I have emphasized that enough, that if you put theory before everything, uh, you will not be able to observe. I think you cannot observe. There are some things like theory-laden observations. Now, for a basic theory, you needed to make some observations. But if you put theory and the rational arguments and logic before observing, you are not going to get anywhere. You might get somewhere, but not very far. Can we go to next slide? Study engineer in the future. This, I think this I got it from somewhere. This means you have to learn, and you have to be multidisciplinary because things are changing very fast. Things are changing very, very fast compared to our time. I'm talking about 50 years ago, 70s when we graduated, things didn't change so fast. Now things are changing so fast. So you have to be crossing borders, multidisciplinary, going from one to the other. And of course, as a professional engineer, you have to be concerned about professional standards, environment, energy, social equity, and ethics. Those are the basic needs of a professional engineer. This interdisciplinary part, I can give an example of from my own career that I passed out as a mechanical engineer, but when I went from my postgraduate studies to do my PhD to UK, I had to shift my field from mechanical engineering to agricultural engineering. So I found a link between thermodynamics and ripening of fruits. My work was on ripening of fruits, but it was based on the thermodynamic concept of entropy and negentropy, the negative entropy. And so my thesis is based on that. It's like actually crossing from thermodynamics to biology. Fruit is a biological process. We have to cross that. We have to be able to cross like that. Metaphor and just as I said, metaphor and analogies have to be used to cross like that. Then I want to finish up these all talk, no, these like ideas. But I want to finish it up by giving two examples of real work I have done, among a lot of other things we have done. These two I want to point out and raise some questions in your mind so that I believe that will help you to become good designers or inventors or innovators or even good engineers. I mean, leave aside these other things. Good engineer, you are first. After all, an engineer is nothing but a designer, right? Engineer is not a bookkeeper. Engineer is a designer. So whether you call him innovator, inventor, or that, those are other accolades that you can use, but you can become a good engineer. So I'll first go the first one. Go to the first one. Most of you will see this and you will roughly know what it is. It is a table tennis table made at home. Buying it would have cost me something like 40,000 rupees. I made it for about one third the price, 4,000, 5,000 rupees. Of course, now you will ask, now we are making a keynote address to inventors of engineering at the Institution of Engineering, but this is a carpenter's job, no? Making a table is a carpenter's job. But do you know that the carpenter has some skills that you don't have, what we call embodied skills, that he can use his body and the fingers and eyes to do something that you and I cannot do. Then I will ask you the next question. what are the engineering aspects of a TT table? Most of you are going, I think it's our level of understanding, you will say you have to get the dimensions right and the thickness right and things like that. I think pretty obvious things you might say. But if you had played table tennis, you will know that there are two parts of playing, that is spin and bounce. Like in cricket, when you bowl, it's a spin and bounce. So how do you get spin and bounce from a table for the required amount? Huh? How do you get required amount of spin, required amount of bounce from a tabletop? For that, you know engineering, but then the problem is you can't cross define. For bounce, you have to know coefficient of restitution, right? Coefficient of restitution is a thing that gives bound, that is a hardness and whatever. Then for the spin, you have to know the coefficient of friction of the tabletop. If it's very smooth, it will not spin. If it's too rough, it will spin too much. So these are standards given for a TT table. So if I'm making a TT table, I have to find out coefficient restitution and friction of the TT table, and I have to make some innovations to make during measurements. That is also innovation, not making the TT table. Making these measurements to meet the standards is also a kind of innovation. I made some homemade things to measure friction and measure what you call friction and restitution. Restitution. Restitution is how much it bounces. Okay, I'll go to the last slide. My time is running out. Last slide. So you will identify this. When we are young, we were on the estate. We used to call it Sangili Palama. Some of the students from Jaffna will know the language. Sangili Palama is the swaying bridge. Swaying bridge, Sangili Palama. And why was it built? It was built for students to cross from the canteen area to the lecture room at the Open University Navada, where we have a stream going across, about a 50-foot wide stream, a canal really, not a stream, going across the campus. So I built this. Then of course you will ask, what is this? These are mechanical engineering design, these are civil engineering design or structural design, because bridges come under civil engineering, na? As to that's what you are taught. But what is the engineering component of this design? These normally you would call it a suspension bridge, but technically this is called a suspended bridge. The difference you have to observe. The difference is in a suspension bridge, the deck on which you walk or you drive for cars is horizontal, but in a suspended bridge, the deck is a catenary. It's a hanging. It's a curved deck. You can see if you look at it carefully, you can see the deck is not straight. It is the catenary. So the cable, what you see on top is not the cable. That is a handrail. That is just a rubber rope that I put to prevent people from falling. That is not taking any load. That is just an ornament. The real cable, the real catenary, is at the below the planks you see. Right? The design criteria for this bridge is just one factor. That is sag of the catenary. You have to work out the sag at the center. That will define the tension of the cable. Then you have to select the cable with the correct tension. Of course, as I use old stuff, reused stuff, I have to use a very large. Normally, a steel cable uses very large safety factor. Even in normal use, they use something like 8, 10. So I use, if I remember right, I use safety factor of 15, unheard of. But as if I use cable, I use, and also because people are going to work on that, and students, I don't want any injury, anything to happen. So I use a very large safety factor. No, I use these two examples to tell you, like engineers, I don't want to get too involved in this word, innovator. As a good engineer who's a designer, don't look at things on face value and say there are no engineering in it. That is why I showed the TT table. The other one, don't look at it and say this is too much. This is far too many involved calculation. Let someone, a specialist designer, or someone do it. No, you have all you have to do is old handbook, engineering handbook will give you the cable tension and the sag. That's all you have to know. You have nothing else. And to tell you the truth, I got some help from another engineer, Mr. Jasinger, to drive the 4-post using a file driver, not a big file driver, small file driving mechanism to drive the 4-post. The rest of it was done by me with my own hands, my technician at the university, and one of our laborers do the heavy work. And the three of us did this in less than a week, believe it or not. And it cost maximum because I got the rails from CGR, cable from the STC, plank from someone else, some importer. It would have cost in all about 3,000 to 4,000 rupees to build the bridge across a 50-foot stream. Thank you very much. Okay, bye.
Thank you very much, sir. The session was truly enlightening, and your never-ending inspiration will be a motivating factor for our entire virtual audience. But a simple thank you is not enough to appreciate your encouraging effort. So I cordially invite Dr. Dulini Modunkotua, the Secretary of ISL JIY Committee, to award the token of appreciation to Dr. Gamini Kulathunga. And once again, I cordially invite Dr. Gamini Kulathunga to accept the token of appreciation.
Virtually.
Thank you very much, sir. There's nothing I can give you, but something will be posted to you.
Thank you. I must say thank you. And I also must thank you for asking me to do the presentation. So that gave me opportunity to talk to young people. When I say young people, you know, there's a difference of 50 years. I'm sure none of the computers were even born at the time I graduated. So sometimes what I talk must be a bit or a marakaratte type, right? I can't help it. Okay. Thanks you.
We enjoyed it, sir. Thank you very much.